Right. That's okay. Why are you shouting? All right. So I'll start with this picture. There's a caption, but without looking at the caption, be honest to yourself and without looking at the caption. Can you tell me what might be going on here? The picture. Any guesses, anything will be fine. Nebula, right? So
Supernova.
supernova. Yeah, so we are already getting the jargons. Nebula, supernova.
Something that happened after that explosion
Explosion of?
of the gases.
Yes. Supernova, nebula, explosion of a star. Right. You want to say something? Nebula. Right. So now what is the nebula? Right. And what is the supernova?
Supernova is when the outer layers of the star are suddenly that the radial pressure exceeds
More jargons. Radial pressure and gravitational force.
when a star dies with a bang.
Star dies with a bang. Yeah, the bang is also another word.
There's a certain type of explosion, and then that leads to an explosion, and all the matter is carried out.
Right.
That's what is
So you're trying to understand the explosion, and he also brought implosion into it. So what is implosion? That's fine. Any other words? But the thing is, this is a beautiful picture, colorful picture, right? And this is interesting. So at the end of the lecture today, we will try to answer this again, right? What this could be. And at the end of the fifth lecture, we should definitely tell what it is, right? So let us see. Now I'll go back to the slide number 1. Right? I'm Gurudat. Disclaimer. My training has not been in astronomy and astrophysics. I only started doing astronomy during my later part of postdoc. My PhD was in plasma physics. Postdoc was also most of the part in plasma physics, and then finally, good thing is we have the slides are visible now.
Yes, sir.
Okay, that's great. Sorry for the interruption. Right. So we wanted to start with discussing the difference between the astronomy and astrophysics. Anybody wants to try?
सर एस्ट्रोनॉमी मतलब कौन सा स्टार कौन से पोजीशन पे है या पे गैलेक्सी कौन से पोजीशन पे है इसका डाटा
Yes. So astronomy is mainly about knowing the position and sometimes speed also. Not sometimes, but most of the time speed also of an object in the sky. Right? So it is basically any object which is outside our Earth. The word astro means big, right? Something which is very, very big. Why do we call it big? Because when we are moving outside the Earth, we are already going to the length scales which are very, very big. Right? So, right, astronomy is the science, you can call it science, which studies the position and speed of an object in the sky. Right? That's the simplest definition we can give. What about the astrophysics? Are they same? Are they different? Formation of the same object. Or basically you apply the laws of physics to study the past, present, and future, right? If some phenomena is happening, if you're observing something, why you are observing that? What will happen? What will be its dynamics or evolution? That's astrophysics. So in the modern context, people say that there is no difference between anything because when you see something, you want to know why it is there, how long it will be there, where did it come from, and so on. So nowadays, people say that there is no difference between astronomy and astrophysics. And sometimes they are also, the terms are also used interchangeably, astronomy and astrophysics. And then another definition, you can say that astrophysics is a branch of astronomy, where you apply the laws of physics to study the object. Right? You can make the models, you can write down the equation of motion, find the solution, and so on. Right? So astrophysics is a kind of branch of astronomy. Could there be other branches? Like cosmology is one.
Studying the chemistry and weather.
Yeah, so we have astrophysics, so we should also have astrochemistry, astrobiology. We also have another fascinating areas, astrovirology. Some people believe that all the viruses they came from this space, right? And then we also have astrostatistics at the lecture we had last time. Meteorology, astrogeology, right? You found some asteroid and you want to understand the composition of it. And then you try to predict where it might have come from, what would be the conditions in past, and so on. So astronomy is a huge area. You can apply any science to it, and maybe economics to it, right? Because people say that the gold, platinum, silver, whatever we have here on Earth, which basically determine the economy of any country, they were all originated in the stars, processes in the stars, right? So if you could take a spaceship and collect those gold or platinum from the space, come back here, you can build your own island. Right? Astronomy, yes. Anybody on the online? Somebody, yes, they wrote something in chat. Yeah, yes, okay. So astronomy is a big area, and then you might have come across other terminology. For example, radio astronomy and radio telescope. So telescope is another word. We will discuss that also in the second lecture. Optical astronomy. Do we have other astronomy similar to that? Gamma ray astronomy, X-ray astronomy, microwave, infrared. What are these? Yeah, these are basically a different frequency band in the electromagnetic spectrum. So the information is coming in different bands, different part of the electromagnetic spectrum. That's how we know the universe, right? The information might be coming in the radio waves, the form of, and the good thing is all of them travel at the speed of light. They are very, very fast. Nowadays we have gravitational astronomy, which are completely different from the electromagnetic astronomy. So far we knew about the universe via those electromagnetic waves. Now we will be probing the universe using the gravitational waves. Right? What are the other waves? You know? Microwaves. That's a,
Matter waves.
that's a cosmic microwave. Those are again electromagnetic waves.
So the cosmic scale, I don't think there is any other wave which we use other than the electromagnetic spectrum.
Yeah, sound waves are also there. But the unfortunate thing with sound waves is they do not travel in the vacuum. They require a medium to travel. And that's a huge relief. Why?
Could result in a lot of
Noise, right? You are sleeping at the night and there's some explosion in the space and you suddenly wake up to that noise. What happened? This is a blessing, right? Which nature has given given to you so that you can sleep quietly.
Matter waves.
Matter waves, yeah. Sound waves are basically the matter waves. Astroparticle physics. We are talking about waves. Yeah, astroparticle physics. That's the astrophysics, branch of astrophysics.
study of expansion.
Yeah, study of expansion of universe. That falls under the cosmology. Cosmology means when the scales are really, really big. The quantities are very, very big, right? Time scale and then length scale are both very, very large. So Big Bang, expansion, right? Those are really, because this space time is also expanding, but we do not know, right? That will be very, very tiny number to be observed. If you want to make it sizable, then you have to look for larger part of the universe. What else? You'll have to be a bit louder for your friends online.
Passes through a very dense plasma. And it does that evaluation. And like was an article which was from around 1980 or 90. But we had it several years. Right? Much from the
Right. So he gave us another clue that information can come to us in the form of electromagnetic waves, in the form of gravitational waves, now in the form of neutrinos also. They also carry a totally new information, complementary information, and the cosmic rays. Sorry? Yes, neutron interaction of neutrinos with materials.
like there is that evaluation happening inside the universe.
Yeah, good thing about physics is that nothing is permanent. Your understanding evolves, right?
Astronomy told us that neutrinos have mass.
Yeah, somewhat there are arguments over that. People say that neutrinos are massless particle, but then there are theories which say that.
Observations, so we can
Right. Right. So those kind of things. So these four things: electromagnetic waves, gravitational waves, cosmic rays, and neutrino. They are the source of information for us. And in combined, they are known as the multi-messenger astronomy. Right? They are the messengers of the universe to us. Imagine. So we are really on a very, very tiny island in this big universe. We don't know that. Do we have any other counterpart also? Are there other planets where we have human beings or life? Whether this is such a fascinating sight that we are sitting in a very, very small part of this universe and trying to figure out what is happening out there. Right? So that's astronomy. And astronomy begins the moment we look up to the sky. Right? With the naked eye itself. And we start wondering what is there, how far they could be, why do they look so small, what could be happening there, right? Are they still or they moving? We don't know. Are they cold or are they hot, right? How shining they could be, where do they go in the morning time when the sun rises, right? Those kind of things are already there. And then astrophysics is there. And there are And the good thing about astronomy is you don't have to be expert to do the astronomy. There are several amateur astronomers also. So if you have interest, and you can learn and delve into that field. But to do the astrophysics, you should really know some physics and mathematics, some computation, some experimental techniques, all those things you should know. So is this enough for the difference between astronomy and astrophysics? And it has nothing to do with the astrology. All right. So scope of the astronomy. This I have taken from this wonderful book. I will say wonderful, wonderful book. There's a website, OpenStax, and there's a book on astronomy, written by the expert in the field, the big team, up to the date articles, information. Very nice book. I recommend that as a resource also. So the scope of astronomy, we discussed few things, but let us try to cover whatever should fall under the astronomy. So observing the sky, the birth of astronomy. We know that astronomy is not of today's science. It is way back. It started with Kepler, Galileo, Copernicus, all kind of people are there. So there's a good books on history of astronomy itself, right? How we started doing the science, right? How we started questioning the religion, and so on. So the astronomy start, as I told you, starts with observing the sky. That's what we have to do, right? And how do we observe the sky for? How do we observe the sky with? And what do we look for? These are basically the two questions here, right? And then where we should look for. Sky is huge, infinite. What is infinite about the sky? Imagine that, arc angle, exactly. So you can imagine that you are in the center of a sphere, right? So, and the sphere has a radius. So your distance from the center to the surface of the sphere is the radius. Now imagine that there's some object on the surface of the sphere. That object will make an arc, and you will make an arc angle with that. So if you keep on increasing the radius, even in the very, very small arc angle, you will find hell lot of number of stars and objects. Right? What do we mean by increasing the radius? It's basically our reach to look that deep into the universe. That's what. So there is no limit to that. Right? You can keep on increasing the power, I will say power or sensitivity of our telescopes and detectors, and we can keep looking to further and further deep. There is no limit. Even in a single arc second, you can see hell lot number of objects, right? Because you know that this simple example, if it is here, then we know that this object is here and it's making a very large arc angle. But if I take it far away, then there will be more object in the same arc angle. That we know. And then there's a unit to define that distance. Those are very, very big units. Parsec. It's a parallel. It's a parallax second. Why do we call parallax? You know, because when we took this object here and I look at from one of eye, this object looks here. But if I look at using this eye, and its object has shifted. So same happens with the Earth also. If you have detector on the Earth, then Earth will rotate around that object. So when it is on this side of the object and on this side of the object, we see that shift. The parsec is basically the distance at which makes basically a 1 arc second angle for that object. That's an parsec. So, and it's a big, very, very big unit. This is a unit of length. And this you can get an idea from this also, that how the resolution and distance are related. You all have seen the traffic lights, right? So if you look from far away, it looks like a continuous number, 7. You're not able to resolve between the two LEDs because of your distance. If you go close, now you reduce your distance, you will be able to distinguish between the LED. You will say, oh, these are the discrete lights. Yeah. That is the same thing with the fluid and particle. Ultimately, a fluid is a particle, but you are working at that length scale at which you really do not care. You can treat this as a quantity. Same thing happens. There are the resolution limit and there is the resolving power. So those are inversely proportional to each other. What we have to do, we have to keep on including the resolving power. We'll discuss that in the telescope section more, but this is also kind of small telescope, right? You know, there are zooms also. So that zoom in we want to collect more and more light. We want to zoom more and more deeper so that we can really see clearly what is there inside that building. Right? But that's not a good practice. You should not look inside the building. You should look up to the sky. All right. Orbits and gravity. These are also the initial thing, right? Which Newton established. We know why the planets are in the orbits around the sun, right? Because of gravity, right? The same gravity which pulls you here. That was also a great philosophical, I'll say, leap, right? Yes. Celestial and terrestrial gravity. So that was the first unification of it. Right? And people say that it basically, sorry, and that may look like a small thing, but that was a huge chunk. Can you say why? Because that at least tells the laws of physics, they are same in every part of the universe. Otherwise, imagine how things would have been difficult. That in this part, laws are different. In another part, laws are different. In another galaxy, laws are different. You really cannot say there are no laws basically. The good thing is that laws of physics, let it be gravity, let it be electromagnetism, let it be nuclear physics, all the two forces, they work in the same fashion throughout the universe. Fantastic. That really helps us to learn more and more about universe. Right? Earth, moon, and sky. Yes, the moon is the first thing we can encounter, right? With the naked eye, without any instrumentation and telescope. And it is so clearly visible and so often visible that people have really used and abused it, right? People used moon to write lots of poetry, right? Some people saw the faces in the moon, right? And so on. Some people worship the moon, right? Some people thought that moon has enemy like Rahu and Ketu and so on. Right? All kind of things are. Earth, moon, and sky, right? So that's the moon is our nearest neighbor outside our Earth. And then when we look further, we come across the other planets, right? So we are now, I use the word planet. So what is the simplest definition of a planet? Yeah, school में जो सीखते हैं. Planet, and what is the moon? It's a moon. School में हमको sub planet बोलते थे, but now all the sub planets are called as moon. Saturn has these many moons, Jupiter has these many moons. So we call something that orbits around planets. And planets are something that orbits around star. So 3 objects: moons, planets, stars. Right? And each star has its own planets and their own system, solar system kind of thing, right? And then what is the another object beyond the star? Galaxies, cluster of stars. And then galaxies also, there are so many galaxies. Yeah, super clusters. My God. And then there is another more exotic objects. There is a black hole at the center of every galaxy. Right. So those objects we will be talking about here. And then there are neutron stars, dwarfs, then pulsars, quasars, nebula.
Results are like some quite interesting. Quite interesting for bit of like Jupiter's.
We'll come back to that. So these are the bodies which we know. But then there are other things which are not classified into planets, stars. These are the comets and asteroids, right? Which are basically remnant of either they have broken from some planets or star, or they are remnant coming from different part of the traveling from one place in the universe to another place. Debris and so on. The sun is a star, a local star. Planets outside solar system, the stars, between the stars, yes. So between the stars we have gases and dust. Right? You will see these are very, very critical. The studies of gases and dust is very, very critical. Then the galaxy, our local galaxy, it's a galaxy is our kind of town, right? So we are in the Milky Way galaxies, then there are other galaxies, and then there is the observable universe. We'll also learn what do we mean by observable universe. And then the Big Bang. So many interesting topics. Right? Each and every topic is really interesting. Basically, we started from our Earth and went as far as we could. Right? So this is a beautiful animation and the picture also, which I will show. So the numbers are very, very large, and it is not. I mean, it's not wise to use 1 lakh kilometer, hundreds of lakhs of kilometer, and so on. So what is the notation we generally use? We either write the numbers in the terms of 10 to the powers of 10, or we devise the new terminology, new scales to take care of those big length scales and time scales. Come to that. So this is the overall scope of the astronomy. In the 5 lecture, what we will be covering, because it's impossible to cover everything. Astronomy, you can have first course on astronomy, you can have second course, third course. Yeah, at least 3 courses you can have in astronomy, and then you can have specialized courses. There's no limit. But in 5 lecture, we will cover this much only. First lecture will be overview, right? Where we will try to motivate ourselves. What we should study, why we should study. The second lecture, we will discuss the most important part of astronomy, that is the astronomical instrumentation. Right? Because those are our tools. We need to design them. Then only we can gather the information. And then there are, as we discussed, there are many objects in the universe. But the most interesting ones are the stars. Why are they interesting? Yes, exactly. Because these are the source of energy, or the radiations, or the light, or the radio, whatever. Those are the interesting objects. The planets and the moons and everything, they are basically getting lit by the lights of the stars. Right? That's how we see other objects also. So these are the basically candles in the dark universe for us, right? अगर ये बल्ब बंद कर देंगे, लाइट या सन बंद हो जाएगी, we won't be able to see anything, and we really don't know anything about this room. But now, because of this light, we know that there are so many chairs, tables. If I go in this way, I will get distracted, and there's a ceiling which is that much high. There's a door there and everything. The stars, right? And their name is also very good. Star. They are the celebrities in this universe. And the sun, because this is our lifeline, our local star, the ultimate source of energy for us to do anything, including this university. The mandate of this university is energy studies. Right? The amount of energy we can get from sun, no other source can use that energy. We will discuss that also in one lecture. And then in the end, as I told you, that data analysis is also very, very critical. So we will discuss what kind of data sets we get in astronomy, right? This could be in the form of time series, right? You are seeing the voltage and current signal continuously in time, or they could be in the form of images, they could be in the form of spectra, and so on. So what are the data sets? And they depend on the kind of instruments you develop, right? For example, this camera, this gives you the images. There's no time series. But if I'm doing some experiment in the oscilloscope, for example, then I'm basically recording the time series, the sign or some kind of signal which is varying in the time. And then the spectrum also. To study the universe, we have to depend upon, first of all, the objects which are outside our Earth, because there's no way we can create any of these objects in our laboratory. At least not in near future. And second thing is the kind of energy they carry. We have to depend upon that. What is another reason? Because there are processes also, which are also not really available on the Earth. I lost my thought process. I'm sorry about that. There was another point I wanted to mention. But that we will come back to that later when we discuss the data analysis. Right? So instrumentation will determine the kind of data we collect and then kind of methods we need to use develop for data analysis. Because it is not simple that you took a photograph of black hole and you know that there is a black hole. No, that's not possible. Lots of different kind of instrumentation is developed, lots of different kind of data is collected, lots of data analysis is done, lots of physics is explored. Then only you come to that conclusion, right? So the textbooks we will be referring to are these. The first and the most interesting and important one, especially for the people who are going to have this for the first time, is this by book at openstacks.org. So they have other useful books also. They have books on science, they have books on mathematics, limited books. Those are most of them are very, very good, if not all. The astronomy book is very, very nice. Second book is by Introductory Astronomy and Astrophysics by Zilic and Gregory. And this is the book I referred. There are other good books also, but this is the book is suggested by the MIT Open Courseware also. They have to use this book to teach their students. And the last one is by our celebrity cosmologist, astrophysicist, Thanupadam Naval. Unfortunately, he expired last year. Fantastic researcher, teacher, person. Right? So he wrote these 3 volumes on theoretical astrophysics, 1, 2, 3. He is from Ayuka. He was from Ayuka. So as a beginner, you should focus. You should also read them in that order. First book, second, and then third. If you directly go to third book, you will say, oh, astronomy is same as the astrophysics, because he has discussed those kind of things. So let's start with our lecture 1. I'm throwing so many things on you. So this lecture is taken from chapters 1 and 2. I will try to cover as much I could, but if I leave something, I will suggest you to go and read these chapter 1 and 2, right? To get a starting idea, initial idea. So what we know about astronomy, we already discussed a lot of it, right? But then there are several things which we really don't know. And we cannot also recall everything right now. For example, I remember the two things we missed. What did we miss? Dark matter we missed. And then dark energy. So what is dark matter?
Dark matter is the phenomenon in which there is more gravitational, there are more gravitational effects for a given galaxy that we can account for.
Right.
The planets are there, that the galaxies are moving at much greater speeds
than they should be. Right. Right. So dark matter is supposed to be the region that galaxies are intact. Right. The planets at the edge, they are not leaving the galaxy. And then the gravitational pull, they exert the two, I'll say, big object exert on each other. The gravitational pull came out to be larger than that which we can calculate from the Newton's law, m1 m2 r square. That is the simplest explanation. That if you have two objects and you try to calculate the attractive force between them due to gravity, that will come out to be larger than what Newton's law gave. But that means there is something in between which is not seen. And why it is not seen? Because it does not emit light. It does not absorb light. Light means any kind of reflection. Also, it does not interact with light. Anything, no interaction. Interaction is neither emitting or absorbing. You really cannot see. Right? But if something goes up, then you saw the deflection. So those deflection also gave you some idea. There is a matter, dark matter. It's pretty much because the baryonic matter we know is only 5%. The dark matter is roughly up to 3 times of that. To assume that 15% of the universe is made up of matter and dark matter, and the rest of that then is basically the dark energy. That's the total source of energy, equal to mc square.
सर डार्क मैटर बेंड कर सकता है क्या लाइट को?
Dark matter, yes, it can bend the light because of its gravity. It can bend.
The example for this question would be the gravitational lensing phenomenon.
Yes, gravitational lensing. All those things we will discuss when we discuss the stars. Not all, some of those things. Yes, but yes, light can bend. It passes through a star. But the important thing is, we all have done this calculation that the gravitational force is very, very small compared to the electromagnetic force. If you have an electron-proton system, then the electromagnetic force will come out to be 10 to the power 39 times larger than the gravitational force. Then in typical situation, light should not bend. But when it is getting bent, that means that there's a huge mass. Either the mass is huge or the mass density is huge. It's basically the mass density that plays a role. The large mass compacted into a small area, a small volume. The sun also has a very, very high mass, but we do not see those effects which we see around the black holes or neutron star. Because yes, fine, it is of one solar mass, but its radius is very, very large. So the mass density is not that strong. And we know from GR that it's a mass density that will curve the space-time more and more, not the mass. So when light passes, it's basically traveling through that curvature around that compact mass. And that's why it looks to be bent. And yes, there are signatures of this bending of the light, right? That you are able to see the star which are behind the other star, other object. It was because of the bending of the light. Light was coming while bending. Right? So dark matter. It is also not antimatter, right? Because if it is antimatter, then matter and antimatter will interact and they will produce the gamma ray. That was also not observed. Also not that. And what it is, we don't know. There are several theories, right? People are trying to do that. But all those are theories. There are no experimental evidence of any theory. All we know that there is a matter which is 3 times more than the all the baryonic matter we know. Baryonic matter, why do I say baryonic matter? Because we know that we can divide the particles into two parts, baryons and leptons. And leptons are pretty very, very small compared to the baryons. So most of the mass is coming from that baryons. And then there is the dark energy. How do we know that there is a dark energy?
Look at the expansion history of the universe.
Expansion.
It accelerates.
It is accelerated. That's it. So earlier people believed that it will, because of the gravitational pull, it will eventually collapse. But then that was not the case. There is something which is acting against the gravity. And not only that, it is beyond the gravity, the gravitational pull of all the particle of the object in the universe. So now there are three possibilities. That either it will keep on accelerating forever, or it will go back to a maximum and then may come back, right? You had the Big Bang and you may have big crunch again. Or what is the third possibility? It may eventually come to the uniform speed sometime. All those possibilities are there, which is given in the FRW framework of cosmology. Right? Friedman, Robertson work. For that you need to know a little bit of GR.
And there are other fringe theories like conformal cyclic.
Right. So you could be theory. You could be sure that if there is a one theory, then there has to be another hundreds of theories, right? On the same topic. Even the GR has several counterparts. At least 10 to 15 are supposed to be the prominent theory, right, of gravity. Right. So birth of astronomy, I will say that you look into any other astronomy book, especially the books by Carl Sagan and Hawking. I think they have written a nice, without discussing any complicated mathematics and equations. You can look into that. And there are actually historians also who have written where did all started, and then what was the issues. When somebody said that no, Earth is not the center, it's the sun, then those things you can. The book also covers, but not in a very extensive way. So history of birth of astronomy is a very, very interesting topic to study. And then we know these big units of distance: light year, astronomical unit, and parsecs. And then we again know that there are big parameters again. Diameter of Earth. What is the diameter of Earth? 6,400. That's the radius. So 2 times of that. Right. And then the sun, distance between Earth and Moon, which is 1.3 seconds. Earth and Sun is 8 minutes apart, and so on. Proxima Centauri is the nearest star to us, and even the nearest star is C. It is 4.3 light years away. That means light will take how many years? 4.3 years to travel to it. So in the astronomy, whatever we study, basically we are studying the past of something. Because we are getting the information now which has already happened in the past. It's already a history. The history of astronomy, and astronomy itself is the history. Something has already happened in the far away from the universe. That information took us a very, very long time to reach us. And we are seeing it right now. So there's no way to know what is happening right now. Right? And that was the conflict between Einstein's theory and Newtonian theory. Newtonian theory says that forces are instantaneous. If you make some changes here, this guy will immediately know. But we know no information can travel faster than the speed of light. We have the retarded potential also, right? If we are charge dependent mass or charge or current configuration, if you make some changes there, the changes will happen here. The potential and electric field will change at another point, but that information will take some time. The distance divided by c, that much time. The retarded potential. And here the retardation time is really, really large. How much large? Billions of years. Right? The first gravitational wave we detected, it it came from an event that happened in billions light years away from us. In that those stars collided. This is frustrating, but this is also interesting. But that also help us to look back in the universe, back in the time, isn't it? So we know what might have happened in 4.3 billion light years. That gives us a chance to go back to the Big Bang. Sorry,
Let's say, but the present of let's say,
the present, you know, you're at Earth in your neighborhood. Yeah, but you know, the human quest and human intelligence is infinite. It is slow, it is gradual process, but it is infinite. We'll know everything. But as I told you, whatever you know, there will always be something which you don't know. There will not something, lot of things you know. That's it. So if you really want to look back, what might have happened to the Big Bang, then you have to increase your reach in the universe to collect the light from earlier and earlier and earlier events in the universe. Right. Yeah. So then there we know that there's a Milky Way, then there's a constellation. Do you know what is the constellation? Constellation kya hai?
Project all the stars on a sphere around Earth. The perceived patterns are called constellations.
Right, right. So what all astronomers do, I told you that the sky is huge. So basically they divide that sky into 88 segments, I guess.
Yes.
Right, and they look into that Sagittarius and I don't remember all, but Andromeda. Okay, they're divided into 88 sections. So Andromeda, Magellanic Cloud. So this is also, these are small galaxy. Andromeda is also galaxy. M31 is that cluster, right? That I'm talking about. So there could be M88 up to 88. Virgo supercluster, which is the cluster of stars and so on. Right? And what is this number? 100,000 kilometers per hour. Anybody online? Yeah, this is the speed of Earth. Right? This is how fast we are moving around the sun. My God. And we are not feeling anything. Why? Because the good thing is because most of the space is empty. And we do not feel any friction. Otherwise, life would have become hell. Right? Thank God that our solar system is most of this empty. And this is amazing. Our atoms are empty, 99% atom is empty. Our universe is also empty. Right? If you look between the stars, it's a huge empty space. If you really want to count one particle, then density is so rare that you will have to go to 1 cubic kilometers to get one star. So that's the density, number density, 1 per cubic kilometer. So we are just finely balanced to live on this earth. I don't know. Right? So this is how fast we are moving. And we know then there are other things. There's a receding speed also and so on. We are really moving very, very fast. And thankfully, thank that the density is very, very low. Otherwise, imagine friction agar hota to kya hota. What is this? Yeah, I would have removed these captions. Hubble telescope. We'll discuss about it when we talk about the instrumentation. Because these are the basically technological advancement. These are really at the frontiers of the technology, not only in the optics, in radio, in microwaves and so on. This is where the engineers learn from, right? And they earn lots of money, and that's fine. Scientists they are behind money, but not like the engineers. Why? Because they know they are not going to get it.
This is a beautiful video.
Yeah, so powers of 10. And share this slide and you can click on it and watch this. This will tell you that at 1 HE each power of 10, it is 10 kilometer, 100 kilometer, 1000 kilometer, where do you reach from Earth? How far away you are and what are you encountering? at that distance. Maybe we can play it, try to play it now. If it could open, allow. Sorry. Oh, so yeah, so these are the slides by a professor in NCRA. Maybe we can go through this also. How to make it full screen? Right. So it's not kilometers, it's 1 meter. So this is 1 meter, right? The stall of a conference. School, right? 10 to the power 0. Then you have to go to 10 meter. So this is 10 meter. You're outside that building where the conference is taking place. 100 meters. What is 100 meters here? Yeah, size of the telescope, right? GMRT, yes. I think, yeah, I think the diameter. Then this is the 1 kilometer, right? I think at this height, no, not even that this height. You are slightly lower than this for paragliding, right? Maybe 1 kilometer, I guess. I'm not sure. I've never gone there. This is 10 kilometers. This is the height at which your planes fly. 10 to 13, 14, 15 kilometers. You are not really able to see who is there, but you can, maybe you can see the big mountains and rivers from the plane. But most of the time you see the clouds, badal. Yeah. That's important. This is 100 kilometers already, going up now. This is 1,000 kilometers. You can start looking at these things. But if somebody has come that close from a spaceship to the Earth, and then you can figure out that there's a life on this. People are really enjoying this. Because maybe our city lights and oceans, sorry? No, I see. So people online don't care? Okay, is it okay now? Somebody wrote something. Screen freezing. Is it back now? Yeah. Stop sharing. This is the technology does not come with the advantages only. Right? It comes with the challenges. So this is the video I will share. Yeah, this is not moving. Okay, now. So you can click on this and watch it. This PDF, and there is a YouTube video also. So this is also the same thing has been shown here in the images also. All those figures have been taken from the chapter 1 of this book, OpenStax. The good thing is they have given you the good reference also. So these are the highly authentic pictures. Right? There are lots of images in the Google, and you really don't know whether they are the pictures taken by NASA during the Diwali or really don't know. But these are the pictures you can really trust. Yes, that this is how the Earth will look like from around 3,500 kilometers away from the Earth, which is huge. Where do we get our space stations? किस height पे होता है? Yeah, 800 or something. This is much beyond that. Right? But Earth is a planet, and it gets lit by the light of the sun. And this is just to give you a scale. This is the Earth, and this is the Moon. We have tried to put it on a scale. See how small you will have to draw them. It takes 1.3 seconds for the light to travel between sun and Earth. You can calculate the distance. Then you go farther away. You encounter with the other planets in the solar system and the sun itself.
Other planets other than Earth. suppose Newton's laws were not present in that time. People must have thought about like is there variation of other planets' distance to this system? Is there any problem?
Sorry, say it again.
Suppose you tell that the distance between Mercury and Venus is T1, Venus and Earth is T2, and so on. Is there any relation between T1 and T2?
It's accidental figures.
But not incidental. Because those are numbers related to the stable orbits of this planet, right? Not completely incidental.
Just because something has pattern does not mean it cannot be an accident. It could be an accident.
But sir, they are outcome of stable orbit. So, must have been that, right?
Classical gravity. Classical gravity can have stable orbits at any distance.
Stable orbit and but I'm saying about relation between two objects in this system, not a single object.
Okay. We'll discuss outside. It is slightly, that question has slightly longer answer. Maybe there's no answer, maybe lots of discussion. This is the galaxy, right? Which has billions of stars. There are millions of trillions of galaxies and there are billions of millions of stars in each galaxy. So
So like it's for big ideas for taking the get out of it, right?
you can take selfie also. You can have that stick.
But sir,
Yeah,
like,
but
how can we take the picture of our galaxy? Of the planar picture, projected onto a plane.
I don't think we have been able to. We have been able to take the picture. We can take the picture because the galaxy itself, our own galaxy, is millions of light years away.
We are at like that we are at
This is
scales
just
of our galaxy. Because that it would be possible.
so this picture is, it may not be the true picture,
Yes, sir.
right?
We can observe other galaxies, but we haven't observed our own galaxy.
But yes, we can. But we can really see some part of our galaxy.
So we can see it like this, right?
Okay, your question is more of a geometric. We'll discuss that later because our Earth is not at the center of galaxy.
But yes, so that's what is it towards the tails of our galaxy.
Yes.
So we can have a picture in this.
It's still in the plane.
So it is in the but in spectroscopic methods we can have some picture. Like we
Remember, our Earth is also rotating. We have different angles of view also. Right? So with this geometry, we will see if it is possible or not. All right. So see, we can see some of these pictures, right? What is this? You can see these kind of belts, right? Orient belts and this kind of thing. It's possible. Had you been in the center, then you would have definitely looked at. Because why do you imagine that everything is in the plane and then they will be not going here and there? So this is not. Why do you think that all these stars in this galaxy are in the same plane? Yes. So what do you imagine? Do you imagine that in your galaxy everything is in the same plane, is aligned to you?
all this picture has been taken.
Yeah, that answer I don't know how this picture has been taken. For that we will have to study. I'm really, and these kind of pictures are not taken only from one telescope. I'll tell you. These are basically combination of various images, data collected from. Yeah, and these may not be from all from optical telescope also, right? So yeah, it's not that. But that's a good idea. Rather than building a telescope, we can make a big selfie stick. take photograph of everything. Yeah, but these answers I really don't know. Right? Only NASA and ESA people can tell. Right. So these are, as I told you, there are stars, and most of the star, space is empty between the stars also. And these are some of the radio telescopes. This is just a picture, right? These are spiral galaxies. Spiral galaxies also are very, very interesting objects. Like Milky Way. Yeah, ours is an spiral. And then clusters of galaxies. My God. So these are now galaxies. We are really, I don't know how far away from the Earth, at what scale we are looking at. So this is one galaxy. This is another galaxy. A cluster of galaxies. And then galaxies, they also collide with each other. And some galaxies, the spiral galaxy, larger galaxy, they eat their neighboring galaxies also. Cannibalism. They make them part of themselves. And this is the picture. So we know that this is a picture of explosion of a star. But by looking at the picture, we really cannot see anything. So that's what the purpose of me showing you this picture. If I show you this picture, you really cannot figure out anything. Right? Just to understand this picture, you need lots of physics, information, other things also. You should know who has taken this photograph, what was the instrumentation used, right? In which part of the sky you looked for, how far you could look. Huh? Then only you can say about its physics. And so first thing is observation. To observe. And these are again interesting thing where they are basically trying to say that the universe, you try to assume the universe to be 1 year long only. So most of everything is happening in the month of December, basically. So these are interesting pictures to look at. You can see. But you can see that on December 30th, dinosaurs become extinct. On December 31st, human appear, right? You just arrived.
I think you appear on the last second of the last minute of the last day or something.
My God, maybe. Yeah, so those kind of interesting thing people do, and this makes things very, very interesting, further interesting. Carl Sagan was the master of that art, right? Hawking he has also written this thing, but his philosophy becomes slightly little complicated to the common people. People buy those books just as a fashion. But Carl Sagan book, people can, and another guy, Tyson, Neil deGrasse Tyson, is also. Right. So this is the picture I got. The solar system formed in the month of September. Earth's atmosphere got oxygen in the month of October. Right. First complex life form appeared. Amazing. So these are some of the interesting videos you can see. Powers of 10, the known universe, and so on. So I think that's it for today. We will discuss those things in the other lectures. Are there any questions, comments, something? Yeah, I had many more slides, but I think time to stop. In the next slide, I really wanted to tell you that why the spherical symmetry is very, very useful, right? And how do you define this horizon, zenith, and those important parameters, right? So no, I assume that you already know that. No, I just wanted to show you that the same coordinates we use. So this is a patch in the sky. For example, something happened here in this patch of the sky. So how do we identify that? This is some theta and some phi. So these are the two parameters. Another parameter is the distance. So at least 3 parameters we always have in the astronomy. There are two kinds of parameters in astronomy: extrinsic and intrinsic. Intrinsic parameters are the characteristics of the source or the event. Extrinsic parameters are basically, they depend upon the location of your detector. Right? You can have your detector on the Earth, they are ground-based detector. You can have your detectors in the beyond Earth also. And then there are things for which you really cannot build anything, isn't it? For example, dark energy, dark matter for now, but maybe in future. And then we have neutrino observatory. There are observatory which study the cosmic rays and so on. Right? Two kind of detectors we generally have: Earth-based detectors and space-based detectors. And spectroscopy is also very, very important. I will say, field, because when you collect the light from something, you can really analyze it to predict what could be the origin of this light. That the sun is energized because of nuclear fusion, it basically came from the spectrum, right? What could be the temperature of the sun, came from the black body spectrum. Right? We did not went to the sun. We did not put a thermometer there, right, to find its temperature.
Sir, sir, in particle physics, are there any candidates for dark matter?
You know, the particle, when you talk about particle physics, then you are basically not talking about, first of all, classical physics. You know, all these things which we are discussing are basically classical physics. You're not applying any quantum mechanics. When you go to particle physics or high energy physics, what is particle there? The quantization of field. So we understand things, yes, and we know that quantum mechanics is true. So we can always develop theory, quantum theory, to explain whatever we also. Because all the classical results will be the limitations of that, the limiting case of that. So are there any theories of dark matter and dark energy in quantum mechanics? Could be.
There are 3 to 4 main categories. There are something called axions, something called winds.
All right.
People used to think that neutrinos might form dark matter, but they don't think so much.
Yeah. So the good person to ask this question will be Professor Bhattacharya. He can maybe tell you. Because if you talk me about gravity, I will say it's a curvature in the space-time. If you ask the same question to a particle physicist, he will say it's a graviton. Right? So I'm sorry, I really don't want to make a comment. I really don't know. I'm not read those things also, even from the superficially also. But yes, you can always develop a theory. There is a gravity theory for theory of gravity quantum mechanism. We call that quantum gravity. Right? Two quantum gravity is another variant. And then there is another new thing, string theory, right? Which is different from the two, and then it claims to explain everything. Black holes, gravity. Yeah, so I'm a classical person, right? I really don't do quantum mechanics. I did plasma physics, which does not require quantum mechanics. I did GR, does not require quantum. No, because this particle separation is much larger than the de Broglie wavelength. There are quantum plasma, they are quark gluon plasma, but I was dealing with the other plasmas.
Was very recent article around 2018 or 2019. A nice publication, which was giving quantization in space.
Quantization of space plasma. No, space plasma are the classical plasma. I don't think we need.
The experimental validity of this.
Space plasma you can discuss with classical models, MHD and everything. You don't need quantum mechanics there. We'll discuss this. So do you know last picture? I will leave you with this. This is a very, very important thing. Galileo's telescope. Can you build a telescope even now? So much material, technological advancement. Forget about telescope. Can you build a microscope now? That is easier.
You require certain lenses.
Yes, it can be made, right? Using a big wall system.
So it's a convex lens basically. Right?
You can use a big wall system.
Or the more simplest one would be we can also use a single drop of light and just point a laser at it to look at the constituents or non-microscopic particles.
Right. The instrumentation is very, very important. It's a part, it plays an important part. Not for the theoretical physicists, but still, those physics principles come from theoretical physics itself, right? Because all the telescopes, basically, which phenomena do they follow? Refraction. Light will pass through that. We'll discuss all those Hubble telescope and then James Webb telescopes and so on. And then the radio telescope. These are the two prominent telescopes. And then GW telescope is totally different phenomenon. It's based on an interferometer. Right. Okay. Are there any questions and comments before we depart? Like with it, stop sharing. If there are no more questions, then thank you everyone.